Yesterday we talked about motion of the sky. There are two motions that we talked about. Let's see if I can jump ahead here. The first one is, of course, the daily motion, and the point of yesterday's lecture was to relate the location on the celestial sphere to actual observable quantities, such as where the object's going to rise and set, how much time it's going to spend above the horizon. So that's kind of the daily motion, that 24-hour motion. We want to talk about today how the star's motions change with latitude. We talked about this a little bit, and I'll just very briefly cover it because it's kind of interesting. When you guys come back to your home institutions, things will be very, very, very slightly different from what they look like here, because the latitude will be slightly different. Now, the changes that you will see are so minor that they're probably not easy to actually identify. But if you were able to go elsewhere on our wonderful planet, you would see large changes in the motion of the night sky. I want to talk about the signs of the zodiac. This is actually something that comes up frequently with students, but not so frequently in astronomy. The signs do have real meaning, though, to astronomers, and I want to point out what that meaning is, just because your students will find that kind of interesting. And then finally, we want to talk about how the constellations change throughout the year. We've actually mentioned this, but we'll just solidify that. So, first of all, talking about how things change with latitude, what is latitude? Does it specify position in the north-south direction, east-west direction, or the vertical direction? Don't be shy.
North-south.
North-south, that's right. Students often get this confused, which is why I leave this slide in there. Although lines of latitude go east-west, it's specifying directions north-south. And so that may seem obvious to you, but this is actually a common sticking point for students, that although the latitude lines are going around the Earth like this, it's measuring this way. So we can specify any location on a sphere with a latitude and longitude, which is really handy if we're talking about locations in the night sky on our celestial sphere. We talked last time about how the direction and motion of the stars changes based on your latitude. If we were to take this to the extreme and go up to latitude of 90 degrees on the North Pole, then all the stars that are visible will appear to go around the North Celestial Pole. At any given time, we are able to see half of the celestial sphere, so that's shaded white here, and then half of it is never visible. And so all of this, you can imagine the celestial sphere just going like this, right? All of these stars are always visible for a 24-hour cycle. All of these stars are never visible for a 24-hour cycle. So that's what you would see on the North Pole. Kind of interesting. And this is the basic reason why we have the sun, which in the summer is visible for 24 hours, and in the winter is invisible for 24 hours. Remember that the sun is not tied to the celestial sphere, but instead it actually varies about this equatorial line there. Here's what it would look like. We'll be able to, hopefully if there's time tomorrow, do a much better job of visualizing this. Here's Polaris, the North Star, everything's going around it. Kind of neat. On the equator, as we saw yesterday, the stars all come up at 90 degrees from the horizon, and they will pass over and then set at 90 degrees on the opposite horizon. As a consequence of this, the North Celestial Pole is on your northerly horizon, and the South Celestial Pole is on your southerly horizon. The entire celestial sphere is visible at some point for exactly 12 hours. And so you can see the entire sky. If you guys have ever been down towards the equator, one of the things that I recognize is that the sunsets are kind of terrible because the sun just goes boop, straight down. And so I remember being in the Virgin Islands and thinking, all right, this is going to be a beautiful beach sunset. And it was just over in a flash. And you don't get any of the lovely colors because it's just straight down towards the horizon. It's much less impressive than it is in the northerly latitudes where it's going in at an angle. So on the equator, we have 100% viewable celestial sphere. Everything goes at 90 degrees to the horizon. That's what a panoramic image would look like on the equator. These stars, or this one star, will pass through zenith. In between, we of course have a mix of everything. So some of the stars are always visible, those are circumpolar. Some of them are never visible. Most of them, though, will rise and then set. And so at our middling latitudes here, we're at about 39 degrees north latitude. We have a mixture of what you see on the North Pole, circumpolar stars, and what you see on the equator, stars rising and setting. Importantly here, and this is an important point for this particular situation, the altitude of the North Celestial Pole, meaning the distance, the angular distance from the horizon to the North Celestial Pole, is your latitude on Earth. And you can imagine taking that to the extreme. Let's go to the North Pole again. In that case, the North Celestial Pole is at zenith, which is 90 degrees altitude, 90 degrees latitude on Earth. On the equator, remember, the North Celestial Pole is on your horizon. 0 degrees altitude, 0 degrees latitude on Earth. And so that same basic system works everywhere. So here in Morgantown, the North Celestial Pole is going to be at 39 degrees, a little bit higher than this graph. And at your home institutions, I'm sure it'll be basically the same. Some of you might be a little bit further south, 38 degrees, but not much different from that. At any rate, it's kind of a handy thing to think about because anytime you want to find the North Celestial Pole, you can just look at about 40 degrees off the horizon, go around, and you'll be able to find it fairly easily. All right, now on to our second topic, the yearly motion of the Earth, which is called revolution. The only change that is relevant here is that it changes which stars are visible at night throughout the year, or in a more general sense, it changes the time at which the stars rise and set. So by time in that sentence, I mean the clock time, the time on your watch. We're going to introduce a different time system later that is stable with respect to the rise and set times of the stars. This is kind of interesting, and probably your students won't know this, or at least won't have internalized it. But the revolution period of the Earth about the Sun is not some nice integer. It is 365.242 days, which is why every 4 years we have a leap year. And that gets us to 365.25 days averaged over a 4-year cycle. Unfortunately, that's a little bit too high. So if the year is divisible by 100, so every 25 leap cycles, then we don't have a leap year. And that gets us down to 365.240, but that's a little bit too low. And so if it is also divisible by 400, then we do. And that gets us back to 365.242. And so the leap years are, it feels very regular in a human time scale, But in fact, we have these kind of funny corrections if we hit multiples of 100 or 400. So the most recent time that this came up was, of course, 2000. In 2000, which is divisible by 100, that would mean that we don't have a leap year, but it's also divisible by 400, so we did. So things proceeded normally, and nobody noticed anything. But at 2100, if any of us make it that far, which is very unlikely, we will not have a leap year. Anyway, it's kind of interesting little factoid there. There's probably some extra decimal place after this, that we have to consider if we're going up to like 10,000 AD or something.
Don't they have like leap seconds or something?
There are also leap seconds. That's right. That's right. There are leap seconds. Those have more to do, I believe, with the rotation of the Earth and not the revolution.